Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module Magnetic Materials, a few examples from the paper Functional Materials. The main points which will be covered in this module are: we will be discussing about the materials exhibiting the diamagnetic and paramagnetic behavior. Here we will be discussing two types of ferromagnetic materials, that is soft magnetic materials and hard magnetic materials. Students, we will be discussing the different types of soft magnetic materials like electrical steel, low carbon steel, non-oriented steel, grain oriented steel, nickel alloys, permalloys, carbon, iron cobalt alloys, metallic glasses and nanocrystalline materials. Next, we will be discussing about the hard magnetic materials like alnicomagnets and rare earth magnets. So students, let us start with a brief introduction about this module. Magnetic materials encompasses a wide variety of materials which are used in diverse range of applications. Magnetic materials are utilized in the creation and distribution of electricity, and in most cases in the appliances that uses that electricity. They are used for the storage of data or audio tape and videotape and on computer disks. In the world of medicine also, they are used in body scanners and in a range of applications where they are attached to or implanted into the body. The home entertainment market relies on these magnetic materials in applications such as PCs, CD players, televisions, games consoles, and loudspeakers. It is difficult to imagine a world without these magnetic materials. And yes, they are becoming more important in the development of modern society. The need for the efficient generation and use of electricity is dependent on improved magnetic materials and designs. Non-polluting electrical vehicles will rely on efficient motors utilizing advanced magnetic materials. The telecommunication industry is always striving for faster data transmission and miniaturization of devices, both of which require the development of improved magnetic materials. Diamagnetic materials. While diamagnetism is a fundamentally intrinsic effect in any material, as it is a characteristic response of each atom, the behavior is typically quite weak and is masked by either of paramagnetic or ferromagnetic behavior. The examples of diamagnetic materials are bismuth, beryllium, gold, silver, and copper, whose magnetic susceptibility are of the order of 10 to the power minus 6 and negative, and hence they don't make very useful materials in magnetic applications. Although superconductors in superconducting state have a magnetic susceptibility of -1, the phenomenon is different to diamagnetic materials. This ability of superconducting materials to repel the magnetic field is used in various applications such as magnetically levitated trains. Paramagnetic materials. Transition elements in the D group of elements as well as rare earths have incompletely filled orbitals and hence can exhibit very large net moment. As a result, the compounds consisting of these elements are typically strongly paramagnetic. All ferro, ferri, and antiferromagnetic materials are paramagnetic above their transition temperature. The examples of paramagnetic materials are salts of transition elements such as KCr3SO4 2 12H2O. Rare earth elements are strongly paramagnetic and they possess large magnetic moments. On the other hand, the magnetic behavior of metals is rather also complex and it is also belongs to the category of paramagnetism. Let us take an example, that is iron and chromium and nickel are ferromagnetic at room temperature. Chromium and manganese are antiferromagnetic while the rest are para or diamagnetic. The transition metals are ferro, antiferro or paramagnetic, with those ferromagnetic becoming paramagnetic above their Curie temperature. Ferromagnetic materials. The ferromagnetic materials can be classified into the hard magnets and soft magnets. The hard magnets are those materials having large coercivity and square hysteresis loop. They have very high values of BH product. Soft magnets are the materials having low coercivity and a thin hysteresis loop. They have a maximum permeability leading to low eddy current losses. As we have seen, the soft magnetic materials are processed in such a fashion so that they have a maximum permeability and low coercivity, which leads to low eddy current losses. So changing the defect concentration and the grain size can decrease the coercivity by reducing the pinning of domain walls to make domain movement easier. For example, iron silicon alloys which are used in transformer applications,
the development of a crystallographic texture along the direction of easy magnetization improves the material's performance and reduced the energy losses. However, it shows higher losses as radio frequencies, and in these ranges nickel-iron alloys are superior. Among hard magnets, alnico, that is aluminium nickel cobalt alloys, is a very popular name owing to their high values of BH product. The properties of these alloys can be tailored by heat treatment which affects the magnetic anisotropy. Generally speaking, ferromagnetism is not found in ionic compounds, especially in oxides. Two rare examples of oxides showing ferromagnetism are CrO2 and EuO, while chromium oxide, that is CrO2, is ferromagnetic at room temperature, that is Tc is around 127 degrees Celsius. The Curie temperature of UO is 77 Kelvin. In rutile structured CrO2, the Cr4 plus ions are located at the body center position and at the cell corners. The spins on these ions are aligned in a parallel manner, rendering CrO2 ferromagnetic. The ferromagnetic behavior of CrO2 makes it suitable for various applications in magnetic recording tape. Soft magnetic materials. Typically, soft magnetic materials are useful for various applications where eddy current losses need to be minimized, such as heavy-duty flux multiplier cores used in transformers, generators, and motors. To keep the weight down, these machines need to employ materials with high flux density, and hence iron makes a very good choice of material and are typically used at 50 to 60 Hz, the frequency of the electric power. In addition, for applications requiring low flux density, one uses iron nickel alloys used typically at lower frequencies. Finally, soft ferrites and garnets are used in microwave range systems. So students, we will mainly concentrate on metallic ferromagnets, whilst ferrites will be discussed separately in further sections.
Students, let us discuss over here about the electrical steel or iron silicon alloys. Ironically called as electrical steel, the iron silicon alloys are one of the most widely used soft magnetic materials in electrical motors. Prior to 1900, manufacturers used low carbon steel for low frequency applications such as in transformers, generators, and motors, which are now replaced to a large extent by iron silicon alloys. They also contain ultra low levels of carbon, which is down to 0.005%. It is also called as electrical steel because these alloys contain up to 6.5% of silicon. The commercial iron silicon alloys typically have up to 3.2% silicon, as higher concentration usually cause the brittleness during their which could be working operations such as cold rolling. In addition, one can add small amount of manganese and aluminium, say up to 0.5%. The advantage of these alloys is that they reduce the power losses in transformers cores by a factor 3 or more. This happens by the addition of silicon to iron, which increases the electrical resistivity to a few tenths of mu ohm centimeters, leading to lower power losses. Also, subsequently, the development of strongly textured steels lead to the development of even better quality of steel, leading to further reduced core losses.
Now, students, here we will be discussing the different examples of soft magnetic materials. Previously, we have discussed about the electrical steel or iron silicon alloys. The electrical steel or iron silicon alloys is of three types. First is low carbon steel. Currently, the low carbon steel is primarily used in applications such as small motors where loss is not a primary concern, such as in vacuum cleaners, it is the cheapest of the all. The carbon content of this grade of steel is 0.03 weight%, which leads to a core loss of 3 watt per kg at a field of 15 kilogauss and an operating frequency of 60 Hz. Low carbon steel is also used in magnetic applications requiring either constant or slow changing magnetization. Some of these can be DC applications, which may include lifting and holding magnets, as well as laboratory electromagnets. Also, for DC uses, one can employ the castings instead of laminated steel sheets. The next type is the non-oriented silicon steel. The development of this type of steel was first pioneered in 1900 by Robert Hadfield, who was an English metallurgist, and subsequently it became a preferred choice as a core material in large transformers, motors, and generators. When one adds silicon to iron, there are significant changes observed. In general, silicon addition to the steel increases its electrical resistivity and reduces the eddy current losses, decreases the magnetocrystalline anisotropy and hence increases the permeability and decreases the magnetostriction, causing smaller dimensional changes. Non-oriented silicon sheets are fabricated by hot rolling the thick sheets to a thinner gauge. This is followed by taking the sheets through an acidic medium in order to remove the oxide scales formed in the hot rolling. Hot rolled sheets have poor surface finish and they are wavy, and hence sheets are cold rolled further to achieve a final gauge thickness whilst also receiving good surface finish and flatness in the sheets. Further heat treatments may be carried out to improve the magnetic properties as well as to alter the carbon content. The next type or the last type of iron silicon alloys is the grain oriented silicon steel. This steel was first developed in 1933 by an American metallurgist named as Norman Gauss. Gauss found that if one employed specific intermediate annealing steps during cold rolling of silicon iron alloys followed by a final high temperature anneal, it resulted in steel sheets with much improved magnetic properties along the rolling direction than in the normal non-oriented sheet. Such grain-oriented steels are eventually called as cold-rolled grain-oriented steels. One can induce the preferred crystal orientation or texture by controlling the rolling and annealing. This typically results in the orientation of the grain such that the easy magnetization direction lies along the rolling direction. So students, let us discuss the second soft magnetic material is the iron nickel alloy. Typically, magnetization of iron and iron silicon alloys is relatively weaker in low fields and they are not suitable for applications such as in communication equipment. The common examples are permalloys, mu metals, and supermalloys. These alloys have higher permeability, especially at lower fields, exceeding a few thousand along with lower hysteresis and eddy current losses. The permeability of these materials is quite sensitive to the heat treatment conditions as well as mechanical working, especially for those containing nickel contents between 50 to 80%, as iron nickel alloys are prone to making the solid solution. Next type of soft magnetic material are the permalloys. The permalloys are invented by G. Elman at Bell Labs in USA in 1914. The permalloys are essentially nickel iron alloys containing 80% nickel and 20% iron, and they exhibit the soft magnetic behavior along with a very high magnetic permeability. These attributes makes these alloys useful for electrical and electronic equipment for use in magnetic cores. They are also used as magnetic shields to block magnetic the fields. In addition to having the high permeability, it also possesses low coercivity, near zero magnetostriction, and an anisotropy in the magnetoresistance. The characteristic of low magnetostriction is useful for a few industrial applications where large changes in the mechanical stress do not cause significant changes in magnetization. Permalloys are typically used in magnetic recording heads and transformer laminations. Next type of soft magnetic material is the iron-cobalt alloy. These alloys possess the high saturation magnetization as well as high Curie point. The application range includes the lenses for electron beam focusing, for use in electron microscopes, pole pieces of electromagnets, transformers, generators, and aircraft motors. Addition of cobalt to iron increases the Curie temperature substantially as well as the saturation magnetization of iron. The last type of soft magnetic material are metallic glasses and nanocrystalline materials. Metallic glasses forms when the liquid metal is cooled from the molten state to the room temperature at a very high cooling rate. The metallic glass alloys, which exhibits the magnetic behavior, contains large quantities of iron, cobalt, and nickel. The alloys shows a maximum saturation magnetization of about 1.5 to 1.9 Tesla whilst exhibiting the low magnetic anisotropy. Metallic glasses are electrically resistive with resistivity over 100 microohm centimeters. Amorphous alloys are used in low-loss transformers and are economically viable in locations where fuel costs are high. The table shows a few examples of soft magnetic materials where they have been categorized as the lamination steel, grain-oriented electrical steel, grain-oriented having high permeability electrical steel, and grain-oriented high permeability laser scribed electrical steel. All the parameters like ASTM number, the thickness in mm, the maximum magnetic field, the losses in the units of weight per lb and weight per kg have been tabulated. Hard magnetic materials. The materials which have highest possible saturation magnetization, high remanence, and coercivity, which are not easily demagnetized, are called as hard magnets, or they can be used as permanent magnets. This figure shows the development of hard magnets chronologically. Over last 6 to 7 decades, industry had seen the development of materials ranging from aluminium, nickel, cobalt alloys to rare earth based magnets such as antimony based magnets, and then neodymium iron boron based magnets, which have yielded the BH product as high as 460 kilojoules per meter cube. Whilst earlier use of a permanent magnetic material was the needle of a magnetic compass, present the list of applications is nearly unlimited. The permanent magnets are used in applications ranging from loudspeaker magnets wherever one requires sound, in small motors, for example, in applications such as in automotive devices, window and seat adjusters, heating and cooling fans, wipers for windshield, small motors and positioning devices in everyday office equipments, example printers, scanners, computers, and similar devices. So students, now let us discuss few examples of hard magnetic materials. First, we will discuss the alnico magnets, that is aluminium, nickel, cobalt magnets. Alnico, as the name suggests, are the alloys of iron, nickel, and cobalt, and also containing the small impurities of aluminium, copper, and few other elements. It was discovered in 1931 by T. Mishima of Japan. Mishima found that an alloy consisting of iron, nickel, and aluminium had high coercivity of 400 oersted, which was nearly double to that of the best magnetic steels in those days. Alnico alloys are ferromagnetic but with a high coercivity along with relatively higher magnetic transition temperature. Hence, these materials shows weak temperature dependence of magnetic properties. The Alnico have a wide range of applications such as electrical motors, microphones, sensors, loudspeakers, and magnetron tubes. The composition of a typical Alnico alloy is 8 to 12% of aluminium, 15 to 26% of nickel, 5 to 24% of cobalt, and up to 6% of copper, and up to 1% of titanium. And there is a balance being iron. Alnicos, they are typically very hard and brittle and are unsuitable for cold working. Therefore, they are either casted or made by powder metallurgical methods. The next type of hard magnetic material are the rare earth magnets. Most of the rare earth elements, having those with atomic numbers between 59 to 70, are ferromagnetic. These elements also exhibit very strong anisotropy in their magnetic behavior. The Curie temperatures of these are lower than the room temperature, making them not so useful individually. However, when they are mixed with some magnetic transition elements such as iron, cobalt, or nickel, they intermetallic compounds which have Curie temperatures well above the room temperature. The development of rare earth magnets started around 1966. As shown in the table that which lists all the rare earth magnets, one of the is magnet is YCO5, which is an alloy of yttrium and cobalt. Another most common compounds, which are antimony and niobium-based magnets having composition of SmCO5, Sm2CO17, and Nd2Fe14 boron or NdFeB. The drawback of rare earth magnets is that they are extremely brittle and are also susceptible to atmospheric corrosion. As a result, usually electroplating or a protective coating is applied for longer or better longevity. As evident from the table, which tabulates the various parameters, that is the critical temperature, the BH product, the remnant BR, and the coercive Hc fields for all these rare earth elements. The SmCO5 exhibits the hexagonal crystal structure with the easy magnetic axis along the C-axis of the unit cell. These are expensive because of the cost of antimony. These magnets are made by melting, casting, followed by grinding to a powder form, which is then formed by powder metallurgical steps to form a final product. Fe14Nd2B are cheaper than antimony-based magnets. These show the tetragonal structure and possess the strong uniaxial anisotropy. They also exhibit a reasonably high Curie temperature. These magnets are also made the similar way as that of SnCO5. Neodymium magnets are used in a variety of applications which requires strong as well as compact permanent magnets, including those in electric motors, for cordless devices and tools, as well as hard drives in computers. They possess the highest magnetic field strength along with a higher coercivity. However, the neodymium-based magnets exhibit the lower Curie temperatures and have higher tendency for oxidation than the antimony cobalt magnets.
So, students, let us summarize what we have learned in this module. First, ferromagnetic materials are further categorized as hard or soft magnets, typically determined by the coercivity of these materials and are the most useful of magnetic materials. Second, amongst the soft magnets, common materials are electrical steels, iron nickel alloys, which are typically used for applications as cores, as to minimize the eddy current losses due to lower coercivity. Third, on the other hand, hard magnetic materials are basically alnicos or rare earth based magnets, essentially niobium or antimony based, latter which is offering high magnetic remnants as well as higher BH value exceeding 100 kilojoules per meter cube. Thank you.